space robots. Right, so next up we have Sean Azimi, who leads the Dexterous Robotics team at NASA's Johnson Space Center in Houston. These are the folks who are responsible for some of the absolute coolest looking robots, I think, over the last decade. You've got Robonaut and Robonaut 2 and Valkyrie, and I have to say that Valkyrie is one of my favorite robots because, among many other things, like it's one of the very few, maybe only humanoid robots that was deliberately designed not to be like some pseudo dude. And I really appreciate that there's at least one of those out there. And I hope you were here yesterday for the Space Robots panel, because it's always fascinating to hear about Sean talk about robots in space, because it's such an extreme environment and all of the requirements and constraints are just totally different from robots that are designed to operate on Earth. But at the same time, you can actually learn a lot by thinking about designing space robots, even if you're not designing robots for space. So I'm very excited to hear from Sean.
Awesome. Thank you so much for that introduction. Good afternoon, everyone. I want to thank the folks from Watney Robotics. That's a really good setup, actually, for my talk, because we're going to start talking about a little bit of teleoperation and the power of that. I'm Sean Azimi. I'm Robotics Technical Discipline Lead in the Engineering Directorate at NASA Johnson Space Center in Houston, Texas. In Houston, as you all know from Apollo 13 and other media, it's the home of the astronaut corps, the home of mission control. So we are focused primarily on robotics that support humans exploring space. I want to start my talk today with the dedication to my colleague Lyndon Bridgewater. He is truly a pioneer and one of the kindest souls that I've ever met, and we miss him dearly. So we'll start the conversation today with a question that is recurring, which is humans versus robots in space. There are a lot of aspects to this question, but I want to start out by considering some of the strengths and limitations of both. So we'll start with the astronaut. So looking at astronauts in space, humans are, as we all know, very adaptable, intelligent, resilient, able to take on many unknown challenges. Is one of the reasons why teleop is so powerful. But working in extreme environments where we need environmental protection, the environmental protection, in this case a spacesuit, when we're going outside, EVA or spacewalks, is a limitation, right? It limits our ability to move primarily because a spacesuit is basically a big balloon. You can see the resting pose for astronauts is like this in microgravity, not because they're doing a zombie walk, but because that's the relaxed position, right? Anything else you do with your arms, to bend your arms or close your hands to grip something, that takes work just to compress the gas, right? And add to that very thick gloves that have many layers of protection built in, and that reduces your dexterity. Looking at the legs, bending the knees, there's not so much use for legs except as an anchor when you're in microgravity. So astronauts are limited by that, but in spite of all that, they're able to do a lot in space that we can't do with the robots that we currently have on space station. You can add to this, right? So the risk of cutting gloves, that creates a potentially lethal risk for depressurizing the suits. And even looking back at Apollo, it's very fatiguing, right? Spending hours in a spacesuit working, it's work constantly, it wears on the body, and while it's a tool that's very powerful, we want to use it on only the most important tasks. Looking at robots, right, we have ways to overcome some of those limitations. We can adapt the robot to the environment to be able to work without requiring the protective covering of a spacesuit. That allows the strength to be fully utilized, the dexterity to be fully utilized. And in addition, robots can be adapted to the environment. For example, Robonaut 2 was adapted, as you can see, in microgravity to have climbing legs, right, that look much different than walking legs, but are adapted with these special crab claw grippers that interact with the same handrails that the astronauts use both inside and outside the space station. So it's a key aspect to us that robots can operate in human environments designed for humans using the same interfaces and the same tools, right? So we don't have to have duplication. But that's an adaptability. But of course, it comes at the cost of complexity, right? And I think the point was made perfectly, right? Saliently, if the robot takes more crew time to set up and maintain than what it saves the astronauts, that starts to eat into the reason why you have the robots out there in the first place. So you need to have very reliable robot systems that are maintainable in the field. So I say, if you take a look at that first photo in a different perspective, it's more about robots and humans working together than one or the other, right? The two can be complementary to each other. And I'll give you an example. So looking at International Space Station was assembled in space from many components built by many nations. And there were many parts of it that were designed to be deployed automatically, but that doesn't always go right. You can see there's a big tear in one of the solar array wings. So we had to use a team of human crew members and robots to be able to address this, right? This is a big concern for space station because this is the source of the space station's power. If that array were to tear further and separate, they would lose a significant amount of power. So they sent astronauts out. We had, of course, in our operations, right, it's not just the crew member out there on their own. There's hundreds of people on the ground, engineers and flight controllers and other space professionals that are supporting them, that are in the room. You've all seen Apollo 13, you know some of the engineering backroom stories and support. But there's also their fellow crew members who are inside, right, in the IVA environment that are operating the robot arm. Right? So we already have and demonstrated these combined human and robot operations successfully, right? But we had the whole reason we had to do this EVA was because we didn't have a robot that was dexterous enough, right, to be able to tie together the cord that would cinch the solar array to prevent it from tearing further. So I think this is a case where these kinds of incidents kind of inspired the idea within my organization for the predecessor project of Robonaut 1. So Robonaut 1, the idea was that what if we had an EVA assistant that had the same dexterity and perception, right, as a human, could use the same interface as a human, that could be a persistent asset that we could assist astronauts who are on EVA, and maybe even save some EVAs altogether by being able to send out the robonaut. Of course, I mentioned adapting to the tools, so in this case, the tether hook and pistol grip tool, kind of the space drill. So these are the tools that are already certified for use for EVA and have compatible interfaces for the crew to use. That's one of the reasons why Robonaut took on the humanoid form to begin with, at least for the upper body, right? The idea of bimanual, 2 arms, with dexterous hands and a head with sensors that you can point, right? But the bottom, right, the body, that was adapted to microgravity from the beginning. It's single tendril in this case, and then with Robonaut we had 2 legs. But power of teleoperation, right? This was late 2000s, before everyone had VR headsets. But it's amazing what you can do with that, right, to overcome the edge computation limitations. And in this type of application, where there's an astronaut inside operating a robot outside, we don't have to worry about the communications limitations and latency, bandwidth issues, comm outages, things like that. Fast forward to today, and there's that guy doing much the same thing with a different robot. So I'm the lead of the Dexterous Robotics team, among other things, and my team is focused on using the Valkyrie humanoid today and other robots to do feasibility studies, look at what are additional things that we can do with robots in space to support our new exploration architecture. And so we've got new places to go. We're going farther than ever before with our new Moon to Mars campaign. And as you can see, you get farther and farther from home. That creates issues that makes things more difficult in terms of both transit time to get new material and people, as well as the communication limitations that I mentioned earlier. So looking at comparing Apollo, right, what we're doing now with Artemis is different than Apollo. All the Apollo missions were equatorial on the moon and lasted for hours, not weeks. Single lunar day, right? So sunlight went overhead. Whereas Artemis is lunar south pole, so like the South Pole on Earth, we have the sun at a very low angle going around, and we have very unusual conditions there, limitations with visibility to Earth, right? Because we're right on the edge. There's a little bit of a wobble in the way that the moon rotates, and it's extreme terrain. So just to give an idea of scale, my home city of Houston would fit entirely inside of Shackleton Crater. And if we compare Malapert to Mount Everest on Earth, that's an even greater terrain relief going down to the crater. Another comparison, Grand Canyon to Shackleton, you can see much bigger scale. But this is part of why we're going, right? These regions, especially inside of the many craters that are large and small, never see the sun. And because of that, there are volatile compounds there, resources that are valuable that would otherwise be sublimated into space instantly were they to see sunlight. But that does put us in, it's a little bit hard to see on the thermometer there, but the red line shows from 40 to 110 Kelvin, and that's among the coldest of the temperatures that we would see in the solar system. And then of course if we're in the sun, right, we have much higher thermal loads. So it's really a land of extremes in a lot of ways. But as I mentioned, that's why we're going, right? There's a lot of resources that are there. That's one of the main reasons why we want to visit the South Pole. So everyone knows Starship. It's the human landing, one of the human landing system options. Have to zoom in a little bit to actually be able to see the crew members down at the bottom there on the elevator. And in early missions, it'll be lander, crew go EVA, they walk outside, they take some samples, they go back up, they leave. But in later missions, we're going to have a rover that enables the crew to go farther. This is the lunar terrain. This is the Apollo LRV, but lunar terrain vehicle is the new version of that. And then eventually there's going to be a habitat, right? We're going to establish more of a presence, permanent presence on the moon where we reuse surface habitat assets. But as soon as we do that, that creates a new limitation versus Apollo, where we have to resupply, right? We have to get rid of the trash. We have to bring in all the new supplies, all the new food, clothes, spares for their EVA suits. It's a lot of stuff. And you can't put the habitat right next to the lander. You know why? Because the lander's gonna blast it, right? Anybody who's seen the Starship takeoff or landing videos, you want your habitat to be far away. It might be 5 kilometers away, right? So now you have to get the stuff from the elevator, right? The elevator will bring it down to the surface, but how do you get it to the habitat? You have to load it onto the rover and then unload it from the rover, move all of the cases through the airlock or into the cabin and be able to do that exchange. That might be multiple EVAs. So that's where we see kind of the value proposition for robots, especially remotely operated robots in advance or between crew missions. Because otherwise, if we send our crew members, we're giving them a lot of stuff that they've got to move, and then we're going to have them do some maintenance because there's lunar dust, and we're going to cover up our solar arrays and our radiators. Maybe we'll add a little bit of assembly connecting up their power unit to the habitat, and that's before you even get to the science, which is the reason that we sent them in the first place, right? So anything we can do to get ahead, right, even if robots go slower, in the 11 months out of the year the crew aren't there, that's a huge value add, right? That's billions of dollars. Like if you look at the labor cost on the surface of the moon, it's very high. I don't know exactly what it is yet, but it's very high. But I think space exploration needs many types of robots, right? They might be single manipulators that are integrated with the interior of the habitat to move logistics inside. In microgravity, we might have free-flying robots, right? ISS is going to be retired eventually, and they'll be replaced by commercial space stations. So free flyers are really good. This is Astrobe that's actually designed and built here at Ames. Gives a great sensor platform. They might be multi-limbed robots that climb, right, and can move logistics and do other tasks. or bimanual mobile manipulators that have different types of platforming. Whatever magic carpet gets the arms where they need to be, right? But there's limitations, right? There's gaps from terrestrial to space. Terrestrial, we have more control over the environment. There's the possibility of intervention with a lower cost. But in space, we just have environments. This is an actual picture from ISS, by the way. We have kind of the space version of hoarding. If it costs a lot to bring more stuff, you're not going to get rid of any of your stuff if you don't absolutely have to. And that's the situation we have on the International Space Station today, that we have lots of stuff. It crowds all the open spaces. And of course, we're not going to plug things in. So we're going to have lots of cables. The lighting is going to be iffy. It's a very difficult robotic navigation problem. Dealing with soft bags, right? We use soft bags because when you empty them, they compress and you get them out of the way. If you have a bunch of hard cases, it's not going to work. But that's hard for robots, right? Dealing with something that's deformable. So these are all challenges that we see adapting. And one of the ways you can learn more about that is to look at, a lot of people don't know. I got a couple links on these pages, so it's good to get your cameras out. Otherwise, you can let me know, and I'll send you these links. But NASA has a Moon to Mars architecture, which we update on an annual cycle. It has an architecture definition document, which lists the elements, like lander, habitat, logistics is a new element. And that has use cases and functions, and that's where robotics and automation can fit in. There's also white papers that give more of an in-depth look at some of the key technology areas for NASA, some of the key use cases and needs, right? But still at a pretty high level. Looking at technology specifically, right? NASA has a mission directorate called Space Technology Mission Directorate. It's responsible for what its name says. They rank annually what the technology needs that they feel are the most important, which reads, what do we fund today versus tomorrow, right? So I recommend taking a look at those. Of course, these days, right, I think people sort of assume, right, NASA's doing all this stuff, but really we're not. It is truly a coalition and a partnership. Commercial, international, academic, interagencies. I think our universities are the wellspring of all of our innovation, and startup businesses are what commercialize those technologies. We explore together. Internationally, we can't do it alone. So it's important for us to be able to establish and maintain these partnerships. To that end. There is many of you know, NASA has a Small Business Innovative Research, so does Department of Defense, National Science Foundation. It's our seed fund, right? So this is, if you're looking for funding, this is where you would apply as a small business concern. It starts with a phase one, which doesn't seem like a lot of money, and it isn't. But that paves the way to a lot of different opportunities down the road and ways to build relationships with NASA programs in the future. The subtopics have been released right at the beginning of this month, and the call itself will go live in January. You'll be able to submit proposals, so I recommend taking a look at that. And that's all for my talk. Feel free to reach out to me on LinkedIn. Happy to connect and discuss any kind of partnership opportunities, or just connect you all with, I feel the mission of my group is to help demystify all of the things about NASA that are a little bit opaque. And there's a lot of information that's out there that is actually public, but it's hard to find. So we're here to help you find that kind of stuff. So thank you very much for your time.
We have time for a couple of questions, and if you're on the next panel, can you go to the back and make sure you get your mic? And who's got questions for Sean?
They're sleepy.
Somebody has to be first. Oh, okay. Yeah.
You can go right there. I'll repeat it.
How does NASA think about choosing what to use full autonomy versus having a human either on the ground or an ISS operator to do it? Is there a strong preference to make sure that both go to the EDAs
that's an excellent question. So the question was, how do we decide at NASA whether to go full autonomous versus teleoperation? And the answer is, it depends on the application, of course, right? What our communication limitations and other drivers are. But I like to say that I prefer a scalable approach, right? The idea of having, starting out with a lower degree of autonomy, more human intervention or supervision, and building up over time, right? Because we have difficulty simulating all aspects of the in-space environment on the ground, either in computer simulation or in test facilities, right? And there's always something unexpected that will happen when you're out there. So having the ability to learn and implement autonomy where we're really good at something, but then be able to fall back if something goes wrong, I think, as y'all pointed out in your talk, is very, very powerful.
Have you guys had extensive exploration with non-deterministic systems where you have end-to-end manipulators but you can't actually reason around whether this will do the thing when you invoke it?
That is a big challenge, right? So yeah, for spaceflight systems, we have the concept of certification, right, and testing and verification and validation, and it is an emerging field right now of how we do that for example, machine learning techniques or something that doesn't have a directly demonstrable, like fixed input to output state machine type of. So it's something we're working on, but I think as folks point out, right, that humans are the same way. We demonstrate through training and testing rather than understanding every neuron.
What do you think is the main constraint to getting like thousands of robots building structures?
I think the main constraint is it's a couple things. It's money, right? Investment. Because it's a niche application, right? It's harder to see the market, right? That if you're only going to sell a few units. So I think bridging that gap from terrestrial, like what y'all are doing, which is I think foundational, right? And then getting that model to translate to an in-space application where we can realize some of those advanced capabilities with not $1 billion robot, right? And part of that has to do with, I think, something I was pointing out yesterday, is that you can't have trial and error without error. We have to be willing to accept that sometimes they won't work out, right? And we'll need to send another one. And I think the incremental, especially if you all demonstrate in low Earth orbit, right? It's a much lower cost than if you jump straight to Mars, right? So that incremental approach, I think, is key.
Thank you very much, Sean.